Good morning again, or whatever time it is. Welcome back to Hunky's study. Um, I'll see you tomorrow in class, but I thought we would give an introduction to eigenvalues and eigenvectors. These come in pairs. These come in pairs. So if L of X is a linear transformation, then 3, say, is an eigenvalue for L with eigenvector U if L of U equals 3 times U and U is not 0. So the idea is we're looking for vectors that map to some multiple of themselves. These indicate, if vectors indicate the direction that you're going, these indicate stability directions. And the 3 tells you how fast you are moving in that direction. So this is what we're looking for. Here is a definition. I've used 3. Typically, the Greek letter lambda is used rather than 3. But this is the definition, and this is what we're looking for. And we've done just about enough that we can find these. So let's take a look at a particular problem, and I'll show you how to go about finding this stuff. There's a little bit of theory here, and I'm going to hold you for some of that theory, and I'll let you know later exactly what it is. So let's take a particular example. Let's suppose that L of X, since it's a linear transformation, it's a matrix times the vector X, X1, X2. And let's do 3, 3 minus, how about 6 minus 4? I think that's what I had in mind here, yes. So this is our linear transformation. We could figure out its equation. 3x1 plus 3x2, 6x1 minus 4x2. So there's the equation. And what we want to do is solve M, the matrix, or let's write L of X equal lambda times X for both lambda and X. So it looks like we got plenty of variables here, maybe too many for the problem. I mean, there's X1, X2 here and another one here. But it ends up you can do this. And that's what I was going to show you. Just to make things a little less Greek, I'm going to use the word, or the letter A here, because A is an unknown for us. And we want to go ahead and solve this. And I'll kind of do it theoretically at first, and then go back and find particulars. This is what we want to do to find eigenvalues and eigenvectors, is to solve this. And eigenvalues are not independent of eigenvectors. An eigenvalue of eigenvector A satisfies this equation, and X is not 0. If X is not 0, ends up to be an important factor. All right, so let's take a look at actually solving this thing now. The way this works is you actually solve for the eigenvalues first. So we want to solve L of X equals A times X. I'm going to bring the X to the other side and write this as M, the matrix M, times X. It's a linear transformation, so there is such a matrix. So that's A times X. M times X minus A times X equals the 0 vector. And now I want to factor out an X, and this is kind of key. We've done this before. But when you factor out an X, you are not left with just A here, because this is a matrix, and so you want to put a matrix here, and the matrix that you put is the identity matrix, and it's the 2 by 2 identity, since we have 2 by 2s. So this is what we want to solve, and we want X to be not 0. All right. So it doesn't look like it's much different, but this tells you something. Not M, but this matrix in here, M minus A times I, has a non-trivial kernel. The kernel of this, there's something that maps to 0 that's not 0. So that says that this matrix has a null space, or this linear transformation has a kernel once you subtract this. So, and let's go ahead and look at this. So 3, 3, 6 minus 4 minus A times I, the identity, 1, 0, 0, 1, has a non-zero kernel. And we want to find the A values for where that happens. Now, if you put in an A value and subtract, and you get linearly independent columns, like if A is 0, these columns are linearly independent, then you won't get a non-zero kernel because the determinant won't be 0. The determinant, once you subtract, the determinant being 0 tells you when you have a non-zero kernel. Let's subtract these first of all. 3 minus A, 3, 6 minus 4 minus A. And we want this to have a non-zero kernel. And the key here is the determinant of this is going to be 0 if it has a non-zero kernel. That is, you want to rig up A so that these columns or rows are linearly dependent. And the A's that make these columns linearly dependent are exactly the eigenvalues that you want. All right, so I'm going to erase some of this stuff now and continue. This determinant we can do by hand pretty easily. This times this minus this times this. So the determinant, 3 minus A times minus 4 minus A minus 18 equals 0. Mathematica finds determinants. It solves all this stuff actually, and we'll use Mathematica, but it's good to do it by hand to get you an idea of what you're doing. We want this to be 0 because we want to find the A values for which these columns are linearly dependent, for which there is a non-zero kernel. Multiplying it out, minus 12, minus 3A plus 4A is plus A squared minus 18 equals 0. A squared plus A minus 30 equals 0. Let's see. So A minus 5 times A plus 6 equals 0. And you notice there are going to be 2 possibilities, and only 2 possibilities for A, 5 and minus 6. That's going to be typical, because when you take the determinant of a 2 by 2 with one variable in it, like this, you're going to get a quadratic equation to solve. Or if this was 3 by 3, you would get a cubic equation to solve. So there aren't going to be many of these eigenvalues, but A equals 5 and A equals minus 6 are the eigenvalues. These are the eigenvalues. We don't have any eigenvectors yet, but the eigenvectors are in the kernel. They are the kernel for these particular eigenvalues. And these are the only 2 guys that have These are the only two ones that work. All right. So we have 5 and -6. Let's go ahead and see how to find the corresponding eigenvectors. So A equals 5 and -6. These are the eigenvalues. Now the eigenvectors come in two varieties. A equals 5 and A equals -6. And the eigenvectors are the kernel. And so these are actually called eigenspaces because kernels are subspaces. So the eigenspace for A equals 5. This is denoted E sub lambda equals 5. This is the kernel of M minus 5 times I. M minus A times I, but A in this case is 5. So we'll compute this matrix and then we'll find the kernel of it. So this is the same thing as the kernel of M, 3, 3, 6 minus 4, minus 5 times the identity. A little bit more work on finding what that is. This is the kernel of the matrix, not the original matrix, but minus 5 times I. So -2 here and -9 here. So -2, 3, 6, -9. So this is the kernel that we want to find. So let's go ahead and do it. So this is solve. -2, 3, 6 -9 times x equal to 0. We're going to solve those for x's, and the x's will be the eigenvectors for 5. So to do this, we row reduce this matrix, augmented with 0. Row reduce. Mathematical will do this for you. You need some extra space here, so maybe I'll just rewrite some of this. So if we row reduce this, let's see, I get 1, 1.5, 0, 0. So this will minus 1.5, 0. So the solution is when x1 is -3/2 x2. The solving equations, and so x2 is free. We'll call it S. And so the solutions are all of the things of the form -3/2 S, S, such that S is free. And this is called the eigenspace. And everything in there other than 0 is an eigenvector. So everything other than 0 is an eigenvector of eigenvalue 5. All right, so these come in pairs. 5 has a bunch of eigenvectors. What are they? They're this. These are all of them. The only one that's in here that isn't an eigenvector is 0. And I'll do one more. I'll do this lambda equal 6, or A minus 6, A equal -6, and see if we can find the eigenvectors for that. So that's the There's 1/2. And now we want to do lambda equals 6. Let's minus 6. Let's check out how to do that. So we want to look at m minus a minus 6 times I. So m minus lambda I equals this matrix, 3, 3, 6 minus 4, minus the a value, or lambda in this case. So that'd be plus 6 minus a minus 6 times the 2 by 2 identity. Computing by hand, 3 and 6 is 9, 0, and 0. Uh-oh, this doesn't look good. 0, 2. These are linearly independent, which should not have happened. 3, 3, 6 minus 4. Some mess up right here. I'm going to go and check it out and be right back. Or maybe I'll just check it out right here. So I think I probably found that, find the eigenvalues correctly, 5 and minus 6. So maybe this is lambda equals 6 is wrong here. I'm going to check it out and I'll be back in a second.